not. I'm Gershom. I'm one of the organizers of the New York Haskell Users Group. And just want to thank everyone for coming out again. A couple of quick announcements. This is a different location this month. Next month, we're going to be back at the usual spot. And we won't have the same sort of space constraints. And we're going to be regularly doing the fourth Wednesday of every month, I think, is how we're coordinating it, so we have regular space there for the future. I want to thank Pat for giving us this excellent space for this meetup. A couple other things. If people haven't seen, there's a website now out called the School of Haskell that is from this company, FP Complete, and it's got like interactive tutorials that you can create your own and go through them, and it'll execute the code online and whatever. So it's a really good experience. People, if you've seen IPython or whatever, it's sort of similar. So that's a good way to try out what they have. Hopefully, they're going to give a talk at some future point talking about that, or maybe some other stuff they've been building as well. The Lambda Jam conference was just announced in the last week or so. They've got the space and everything. It's in Chicago in, I believe, July. They're taking proposals for talks now and whatever, or you could just start planning your tickets. They're going to be having a range of talks across all the FP languages, and it's done by Alex Miller, the guy who does Strange Loop, so it should be really cool, and I know they've got a lot of cool things in the works. If anyone else has announcements, they can do them at the end. And now we're going to have our talk by Wright, who I've seen speak before, and is he does all sorts of cool stuff with wireless and otherwise. I don't know how much he'll tell you about. And it's going to be, I'm sure, a really engaging talk. There'll be a short break somewhere in the middle, and then we can sort of come back after we get a bit of math overload and get math overload too. Thank you, Gregory, for the talk.
Thanks, Christian. Can everyone hear me back? Way down. Okay, I'm going to be loud now. I'm Gregory Wright. I'm at Alcatel-Lucent Bell Labs, which generally makes things like 400 gigabit Ethernet and cellular base stations and that kind of stuff. But I'm going to tell you about some work that I'm doing as a sort of side project along with some academic collaborators. The academic collaborators are not working on this actual calculational part. They're radio astronomers. My background originally is in radio astronomy, and their goal is to take a bunch of radio telescopes around the world, link them into effectively a giant radio telescope, and image the black hole in the galaxy M87, which hopefully will tell us all kinds of cool things about general relativity. This is kind of an offshoot of that to try and calculate a few things which might be interesting to observe. The difference between this and most of the other talks that will be given here is, in this talk, there will be continuum mathematics. There'll be continuous functions. There'll be differentiable functions. Not just discrete mathematics.
Are they going to be polynomials?
There actually are almost no polynomials. Because that's too close to discrete mathematics. And the other thing about this talk is that, for some of you, mercifully, there will be next to no monads. I'm going to abuse Haskell in a much different way. Okay, so here's a general outline. I'm going to talk a little bit about how symbolic algebra got started. It's been around for about 60 years now, but has been a laboratory in which functional programming has developed. And functional programming was originally developed to do many of the kinds of tasks that I'm going to show you here. I'll tell you a bit about, and why, and I'll tell you a bit more about, well, why am I doing it yet again if it's been done for 60 years? A bit about the Wheeler library, what it's good at, what it's supposed to do, and how it works. And I'll do a little live demonstration of a few of its interesting characteristics, just to give you a taste of the capabilities. And then I'll show you some results from a kind of real world size test case. And go through in a bit of detail, especially for new people, how you profile something like a library like this, how you find out which are the bits which are actually slow as to the parts that you thought were slow. And in this case, because it made a very good example, because the parts that I thought were slow were in fact completely unrelated to the parts that actually were slow. Then I think about that point we should be ready for a break because you will have seen far too much continuum mathematics. And we'll go back to the comfortable safety of sort of programming language theory and how we would solve the expression problem, which is key to actually making libraries like the Wheeler library a useful tool. I'll explain to you what it means, but the expression problem is key to allow people to build upon this kind of work and extend symbolic mathematic libraries. So we're going to need a solution, at least some kind of workable solution to the expression problem in order to build on this work going forward. So, symbolic algebra programs are the oldest non-numeric programs. They predate the introduction of Lisp. Knuth actually says it's just folklore that they existed in 1952, doesn't actually give a reference. But shortly after the invention of Lisp, symbolic capability was recognized as being very important, and there was the first kind of symbolic math program, really as an AI program, is trying to model how college students actually solved integrators. It was called SAINT by Slagle, 1961, so now more than half a century ago. Then it was followed by the SIN program, which is symbolic integrator, which was a very different approach. This SIN is more just kind of a modern approach to things like numerical integration, so much it's an algorithmic approach. So it's not trying to model the human thought processes, but was trying to be a kind of domain expert. And had a lot of tricks built into it, but wasn't a general solution to the problem. In fact, the theoretical pinnings of a general solution to integration didn't appear until 1968 with the Richard's decision procedure, and then a few years afterward it became partial implementations of it. So those are kind of point solutions. They did one thing well. General purpose symbolic algebra, really to allow people in science and engineering to interact with their equations and try to solve them, starts from about the same era. It really wasn't until Lisp was developed and computers got to be roughly, again, having hundreds of kilobytes of core store, that it was possible to build some approximately general purpose system. One of the earliest designed for problems in physics, the Schoonship, which was done by Martin Veltman. He picked the name, it means clean ship. He said it was Dutch, and he thought it would annoy people who weren't Dutch. It was actually written in CDC 6400 assembly code. But was remarkable in its capabilities, as long as you broke everything down into a sum of products. If you pre-process things into a sum of products, it was remarkably fast, would shuffle stuff off to disk, did all the storage management manually, pre-virtual memory days, but had great capabilities and actually allowed the computation of particle collision cross-sections in high energy physics. So things which were actually observed by the late 1960s. The first kind of what we would consider the modern attempt at a symbolic algebra system was MATLAB, not MATLAB. MATLAB was built out of Lisp, and is kind of the progenitor of all the modern systems, Maxima, Maple, and Mathematica. Maxima was born at MIT, and its idea was to use Lisp to provide engineering solutions to all of the these kinds of problems. So it's very much targeted at something that is good enough for engineers to work interactively with. I'll say something more about that at the end of this slide, because it's kind of important to understand what the state of the art in the field is. IBM came up with Scratchpad, which changed its name to Axiom in 1971. It was the first attempt to do a rule-based system, so like a ternary writing system, very much like you still find today in Mathematica. In Scratchpad, they ripped it out. They found it was very hard for people to write code based upon rules. It was much easier for them to use a procedural language than a kind of more conventional algorithmic approach. Maple was interesting because essentially these folks up in University of Waterloo wanted the capabilities of Maxima, didn't have a computer big enough to run it, so they wrote something which would do the same thing. And it's interesting because it bootstraps a small core, written in C, and then writes the rest of the system in the language defined by the core. And that's, to some degree, the approach that I'll be taking with the Wheeler library. We're going to essentially have a small core which does basic handling of symbols and simplification, and then try and grow the rest of the capabilities around that. SMP was Wolfram's first attempt at a symbolic system. It worked pretty well. It was very much targeted, again, at high energy physics. It had some design decisions which crippled it and made it useless, but it got him into a huge fight with the Caltech people because he made a commercial without giving them any money and telling them about it. Then once he had left over that dispute, he came up with Mathematica. Mathematica originally, the math capabilities were somewhat disappointing. I remember using it basically right after it came out as a graduate student, but its graphics capabilities were unmatched. It really became not so much was used for its mathematical capabilities, but it was used as a data exploration tool for doing statistics. And it's something, eventually, it got enough money. It turned out that market was bigger than people who needed to actually solve equations. That the money from that has gotten it up to being a pretty good, solid mathematical tool. But it is a sad fact that especially in situations where you need to do integrals, which radicals, things which you have multiple value functions like the square root and branch cuts, that the technology of Maxima from the late 60s, early 70s is still about the state of the art. With the development of Maple as a commercial product, spin out from Waterloo, University of Waterloo, with Maxima being spun out by MIT, originally through the Harper company Symbolic, and then on its own. Government funding and university interest in the field dried up and went away. So there was a lot of opportunity here because the field has not moved in a long time. Axiom was interesting because it tried to use types. It tried to be strongly typed and be written in a typed language. Their use of types was essentially to try and provide help for the simplifier to figure out what simplifications could be applied efficiently, so it wouldn't have to search through things. If you play with Axiom, you realize that it sort of works. It does very good for polynomial arithmetic, which is what the IBM people were especially interested in because they were doing crypto. But it's not, for general expressions, it doesn't actually help that much. It would be nice if it helped more. And in particular, one other thing I'm going to make a distinction. What I'm talking about is symbolic mathematics versus what has evolved into computer algebra, kind of separate fields. Symbolic mathematics is what we do when we're trying to solve some equations and massage them into a useful form so we can get information out of them. As opposed to what I would say computer algebra is, which are people who want to who construct various algebraic objects, find things like polynomial ideals. Those certainly good and worthwhile things to do, but they're really heading more in an algorithmic direction. Symbolic mathematics, one of the key things is the interaction, because usually there is not one single solution. There is some kind of class of acceptable forms which tell you what you want to know. So why Haskell? We know Haskell. Now, it's got some libraries in it already, so there is a foundation on which to build. everyone should play with the numeric prelude. It's kind of fun. Everyone should play with the domain the algebraic domain constructor too. If you got a weekend without a lot to do, it's a big package. But these are great things, and it'd be nice if we could build expressions out of these things and manipulate them. It turns out that's a bit harder, and it's harder for some reasons which I'll go into. The other thing is why we like to use Haskell. We like Haskell because it has a syntax which is close to mathematical notations which we like. So it's easy to explain, to express things. It doesn't take a lot of room. In particular, when you go back and look at it a week later, you can kind of figure out what you wrote. And that's one of the wonderful things about Haskell. All right, I mentioned earlier that the mainstream languages, kind of mainstream mathematics packages, locked in the 1970s era. And you can tell that if you have to write an algorithm in their internal languages. They're just old hat. So to build a symbolic math package, there are two minimum requirements. You need to automatically perform the non-controversial simplifications. Okay? So one of the big problems when you do this kind of stuff, and you'll see, intermediate expression bloat. All right? So you have this nice little thing you type in, it's like 4 lines, and then you hit expand, and blam, 38 pages of stuff. All right. So in order to keep that under control as much as we can, we have to take things like, well, here's one copy of this term, and here's another. We need to find out that they're equal and say 2 of them rather than 1. If they're the same, there's a minus sign between them. 0, you get them out of there. Doing the non-controversial simplifications is an enormous simplification. There's some systems which have attempted not to do it, and they just kind of fall over under their own weight. What are the controversial simplifications? Controversial simplifications generally involve things which can go wrong with complex numbers. Log of x times y equals log of x plus log of y, right? Oh, there's a branch cut though. Log of x times y is actually equal to log of x plus log of y plus 2 pi I times something called the path function in some people's notation. It depends on just how you go around the branch cut if the arguments are complex. So if the arguments aren't real and you don't check, you can produce things which are incorrect. All right, and most of the existing big packages will miss corner cases and produce incorrect things. And particularly for these kind of high energy physics stuff, singularities on paths of integration determine the boundary conditions, determine whether or not you're thinking about waves which are going out as opposed to waves which are coming in. So if you screw that up, you get nonsense. And the other thing you need is a pattern matching and replacement facility, because ultimately what you're going to be doing is taking stuff in some kind of form that you don't like and using something to transform it into something that's better. And if you get those two things, you have the core of a numerical, or probably a symbolic mathematics program. Yes?
Is would the difference of 2 squares type of thing also be a controversial simplification?
Positive integer powers are okay.
Well, I mean, there's the question of, do you want x plus y times x minus y, or do you want x squared minus y squared?
That's okay. Things like that are often a matter of taste, and it would be nice if the user could control that. In my the Wheeler library has a notion of one way it likes things, and I thought about having a facility to allow you to do like custom reorderings for display, but I haven't put it in yet. It's important to have a canonical ordering for automatic simplification specification that every expression at least goes through so that you can do the comparisons. Say, essentially what you want to be able to do is if the two things are obviously equal, they should be identified as such so that you can combine them or cancel them. So what are the bees in my bonnet? I told you at the beginning I'm a recovering radio astronomer. And I have this interest in these weird gravitational effects that we might be able to observe if we have a suitably large black hole in a conveniently nearby galaxy. So what do I need? I need a way to manipulate symbolic tensor expressions. I'll go on in just a little bit about what tensors are. We use them in video processors, but I'll tell you a little bit more detail about how physicists like to consider them. And I also need the ability to work with non-commuting objects. Non-commuting objects like matrices, you take square matrices, you multiply them in this order, you multiply them in that order, and the answer is different. And in physics, we have to deal with other things, things like that are just, some things which are just matrices, and they non-commute in a fairly conventional way. And then there are weird things like the objects which represent spin 1/2 fields, like the electron and proton, which if you have one here, then you switch them, they change sign. In fact, we need to keep track of that when we do symbolic manipulations of expressions with those kinds of things in it. There are some software packages out there which already try and do these things. I started this project to solve my bee and bonnet problem using Cadabra. Cadabra is a wonderful, kind of tech-based input. It's designed for speed. It's written in C++. It goes fast. If you're old enough, you'll remember a phrase from the original radio program, Hitchhiker's Guide to the Galaxy. Looks like a fish, moves like a fish, steers like a cow. Pretty much every substantial interaction with Cadabra ends up, although it has many wonderful facilities, some of which I'm stealing and building in, ends in a segfault. Okay? That's the problem, because it was designed initially for speed rather than correctness, with pointer flipping because that's better. And, well, it didn't work out. So, we're going to take the opposite approach with this library, and we're going to try and design things for correctness first, and then make them go fast. Mathematica is a package called extensor, which is great for gravitational calculations, except it doesn't handle non-commuting objects. And it just doesn't do it for me. And to actually shoehorn it in was going to be very difficult to understand how the whole thing was written. Because there's a mixture of algorithmic and rule matching in Mathematica. And so why is it called Wheeler? It's named after John Archibald Wheeler, who probably none of you in this room, anyone know who he is? Oh, a few people here. Princeton professor, figured out nuclear fission with Niels Bohr, was Richard Feynman's thesis advisor. And when I was a graduate student working on my experiment, having spent all night in the shop, he always came in at like 6 in the morning through the service entrance near the shop. He would poke his head in and say, "How you doing?" So he was generally a great guy of the era in science before, when everyone who got a PhD was a member of the club, and we weren't all trying to figure out how to get all the kids to go up on Wall Street so they wouldn't, clog up the postdoc chain. So he was generally a good guy. So we ought to have something named after him. So what are the goals for this package, the Wheeler package? Keep close to the natural Haskell syntax. We love the syntax, we don't want to screw it up too much. So don't do, there are embedded languages which are, yes, it's like a different language. The goal is not to speak Klingon and Haskell. Okay? The user is not a compiler. So I don't want to have to say, well, to do simple tasks like multiplication, powers, addition, I don't want to have to use a different notation. Plus is good for addition. Many people understand it. Which means that, use the natural operator. All right? So this means that for the sake of the user, abuse the type class system to shoehorn things in so they work the way people expect them. So again, take the onus on the library developer, not putting it on the user. Don't force the user to do explicit simplifications. So every time you do an addition, and the only time you get a chance to do the simplification is when you add or multiply. That's a very important design decision, because if I'm not going to force the user to explicitly simplify, then I need to essentially after every operation do a simplification. So it may pay to do the simplifications incrementally. All right, so make sure that you don't re-simplify something that was already simplified. That may seem like a bit of foreshadowing. It turns out that re-simplifying right now is not nearly the worst problem we have. There are other things which make it a lot slower. I, in fact, did put it in and then I ripped it out because it made no difference. I was somewhat embarrassed. It taught me that what we say on the website, the wiki, profile first. Okay, we got to properly treat non-commuting objects. So that's again one of the goals. There will be non-commuting objects in the calculation, and the automatic handling of tensor indices. So when you build these complicated expressions, and they'll have tensor indices. One of the things which we often do is we multiply them, and then we want to sum over this vector component this way, this vector component is pointing this way, and then we'll take some of those things and we'll expand them. We want to make sure that all those indices which are supposed to be summed over are taken care of automatically. Okay? The user can expand things and factor them, and they don't have to worry. Everything gets relabeled automatically. And this, it turns out, if you really start messing around with some of the existing systems, often breaks. Okay, so vectors have to be handled automatically. So what are vectors? Well, it's like magnitude and direction. Okay, they often have other properties. Like the side of this iPhone defines a vector pointing this way. It points toward the spirit of Steve Jobs somewhere in space. Okay? But vectors have this interesting property that they are invariant under rotations of the coordinate system. If I change my coordinate system, the components of the vectors change to keep the vector in the same place. So these vectors all have certain invariances under transformations, typically in ordinary space rotations. Tensors are just objects who have a lot of indices which transform just like vectors. So essentially, they're just grown-up vectors, and if you multiply them with some indices, then leave one unsummed, what's left is just like a vector. And there's a special tensor called the metric, and it computes the length of a vector. And it's important because the length of a vector is the same. And no matter how we change our coordinate system on this iPhone, this side, which always points to the spirit of Steve Jobs, hovering over New Jersey, I think, it's always the same length. So there are invariances built in. So it's important in physics that we preserve these vector and tensor forms, so that the equations we write are always definitely vectors or tensors. So they always have the proper rotational properties. If we don't, we are not able to check the consistency of our intermediate results. And we're going to do a lot of not especially systematic transformations. It's very important to be able to have a check on the consistency of intermediate results. And this in physics is called doing the calculation covariantly. Some of you know a bit more math than you should. Use covariant in other ways. We used it first. Right? But we can talk about this more. And in fact, there is a kind of a sensible reason for why in fact, this index up notation is called contravariant because the actual change of basis is by definition covariant. So this just shows you how we sum up this thing G is a metric, and if you take its components, you sum them all up on two vectors, you get the squared length of the vector. So exclamation sign here. Now, one of the smartest people of all time came up with a marvelous notational convention. He said, if you repeat the indices, you don't have to write the summation sign. This man was Albert Einstein, and it was a brilliant idea. So in fact, all we have to do is write this object in these, and when we repeat an index, it means sum over all of its values. Okay? So, that's how great minds think. You leave out the summation sign, and life becomes much easier. So I'm going to insist that when I type things into Haskell, that happens too. Right? When I type a tensor and I repeat the indices, automatically it figures out that, well, it'll eventually have to be summed. Okay? The other thing, as I mentioned, we deal with, when we sum over indices, we replace them with something called a dummy index, which is this indicator, this index is to be summed over. And when I write things like this, and I expand them out, or I factor them, I want those dummy indices to always be consistent. Okay? And that's going to be a key thing. And finally, I think we have a correct algorithm for doing that. All right, so what are expressions? Expressions are just an algebraic data type. Now, every other people come here and first Haskell, and you're supposed to say, and here's my algebraic data. And of course, it's a function. Well, this isn't. You can't put arbitrary things into it. And there's a reason for that, and that is the difficulty of extending things into which you put arbitrary stuff when you have to examine 2 bits of a tree-like structure simultaneously. So after the break, I'll talk about the expression problem and ways we might get around it. But the basic, the way expressions are going to be represented right now in Wheeler, which turns out to be good enough for a lot of real things, is what we have constants, which are integers and rationals. We have function applications. We have symbols. Symbols can be plain old symbols, x, or it can be a more complicated thing. It can be a tensor. And you're going to have sums, products, and powers of them. And if things go wrong, undefined. Okay, so I told you we were going to abuse the type system to sort of shoehorn things into Haskell. All right, so many things will be instances of num. All right, num is, you can't feel bad about abusing num because it's badly designed to start. All right, we multiply, we add expressions, and so we just stick them into the sum. There's a list of everything that needs to be summed, and then we canonicalize it. So canonicalizing is what puts things into the standard for that we can use to compare. Because every time we do something, we canonicalize it. Also, it has tucked into it the magic to check things like the indices are consistent in a tensor. So subtracting is just sum of a negation. Multiplying is just stuff, the 2 things to a list and canonicalize thing with a product around it. It's these kind of transformations where what we do is we really make everything sums or products. Negation is represented by multiplying by -1, and division is represented by raising to the power of -1. That's just to get rid of the sort of number of different expressions that we have, and that is common in every general purpose symbolic mathematics system. It is an interesting question as to whether it's really a good idea. I mean, I did it because everyone else did, and it seemed to provide a simplification. But I'm not entirely sure that it helps. So if people are interested, and once this thing gets up on GitHub and you play with it, and maybe someone will find a good reason to change that.
Change which part?
That I represent subtraction as the addition of something which is negated, and I represent division by multiplying by something's reciprocal. Okay, so there's reciprocal is in the fractional class, which is there's many classes here. These are kind of the simple ones, just to give you a flavor of how we abuse the type class system. For comparing things to get them into canonical order, yeah, it looks real small. This is top secret for my work, so I had to print it real small so you couldn't see it. The expressions are instances of order. And that was, they don't have to be an instance of order. You could make a special thing, a special class for comparing expressions. It turns out that when I initially did it, made the whole thing work with commuting quantities and then added non-commuting quantities, and it turned out that I could not have a single class for ordering. You can make all expressions, all instances of ordered if they commute. But if you want to have sums be able to, if you're summing non-commuting objects, you have two square matrices that don't commute, well, you can certainly add them in the other order. So I needed another class called SumWord, which would only be used for comparing things inside of sums. So my bright idea of hijacking the ORD class for comparing expressions wasn't so great. But there's, a lot of these things make no sense. They are a canonical ordering. They are not any kind of, oh, this expression is less than that expression. No, it's like, we just do a lexicographic ordering of the terms in a polynomial. It's an arbitrary ordering, but it will find an ordering for the expression so that things can be compared. Things will always go into the same order. Is that going to be your question?
That was going to be my question.
Okay, good.
Okay.
So what goes on in canonicalization is kind of busy, and I show you this kind of call graph because I'll come back to it when we talk about the expression problem. But there's a canonicalized function, and we simplify constants, sums, products, powers, functions. When we simplify products, we actually split it up into their factors and try and simplify the factors. RNEs are rational number expressions, so that just does everything with fractions and integers to combine them and simplify them. There are some recursive calls here, merging of terms and simplified terms, and also simplifying integer powers are explicitly recursive functions. The guts of what goes on though here is in merge commuting factors and merge non-commuting factors, where we split up the factors into all of the mutually commuting and non-commuting sets, and find out if we have to reorder any of them, we do the appropriate transformations. So it's fairly busy. And again, this compare, of course, is from the order class, but in order to deal with sums with non-commuting things, we've got sum class. So it's a word. Sorry. So you can see how, and I'll show you just a little bit how we play with ordinary expressions in Haskell to represent tensors and have a nice syntax. So when you type them, it kind of looks like what you would write in your lab notebook. I'm going to use a function for the kernel symbol, and that function will be applied to indices. And so this makes an index, G makes a metric in Minkowski space, which will, when you print it, will be G. All right? Minkowski space is the space that we live in, the kind of four-dimensional space-time that Einstein talked about. So this is the metric which preserves the speed of light, rather than the length of the side of the iPhone when you rotate it. So it's important for calculations in physics when we make things go fast, or swirl them around black holes and make them radiate. So this is actually the expression taken out of part of the program which calculates the demo problem. So this is a metric tensor with two indices. This is another one times two indices. So you can make sums of products. And when you multiply this times a bunch of other vectors, all of the indices will be taken care of. So you can just write them, like you would write things in your lab notebook. All of these indices, just written as they are contravariant. They're upstairs indices. Okay. I had to wash my hands after I did this. I want to represent contravariant indices too. I could make a function which took the upstairs index and made the downstairs index. Right? But that's ugly. But Haskell has no unary operators except minus. So I made the indices instances of null. So a var index is an index which can be up or down. There's another class which has just plain indices, like for plain old matrix indices, when you want to do matrix calculations. So it basically, if you negate one, which is upstairs, it goes down. If you do it twice, it goes back. And anything else you try and do it, you have this error message because the num class is designed poorly. It works. It's a nice way of just typing things in. And I'll just say it as an aside, one of the really difficult things when using the system for actual calculations is getting things typed in from the notebooks, and particularly as the expressions tend to be fairly long, into the program without errors, especially given that the articles and books often have misprints in that. So I actually spent a lot of time sort of going through and making sure the data is pretty clean before we can actually use it. So here is, you can write things like this. Here's the thing called a Kronecker delta tensor. It's the simplest tensor if the upstairs index is numerically equal to the downstairs index, it's 1, and they're not, it's 0. And it shows up as intermediate form in lots of calculations. It's the tensor equivalent of the unit matrix. And the way we write it after you define the delta, you say make Kronecker delta. You have to declare everything you want. Minkowski manifold says this thing lives in Minkowski space. That's used to check to make sure it's applied to the right indices. Indices know which things they're supposed to be applied to. They live in a certain space. And if you try and apply, say, a tensor kernel symbol, which thinks it's only supposed to be given indices in Minkowski space, to something that's, say, given, well, from a high-energy physics calculation, a color space. Color is the force which holds the proton together. Color space index, it will bark for the runtime error. I can't make the, there's no way we're going to make the type system do that. It's going to bark for the runtime error. At some point, there's a lot of information, in these tensor symbols about the symmetry of the tensor, what happens when you flip the indices, and that can be used for simplification. So you have to declare that your indices, this stuff just tells you what their name are, what their tech name will be when they're printed out as text symbols. And then you can say let G equals delta V. And this means that G is the Kronecker delta tensor. All right, and so upstairs is mu, and downstairs is minus mu. All right, and you had to wash your hands. But it turns out to be very expressive. When you're looking at something in a book, typing it in, anything that's up is just the plain old letter. Down, put in a minus sign. It's half, so you got to put parentheses. Test drive. Okay. I didn't say a lot about developing the non-commuting stuff, but that actually turned out to be a pretty big challenge. If you rip into the source code of the open source systems, where you look at the published descriptions of the simplification algorithm, so there is a textbook one. It's given in the references at the end. A man named Joel Cohen, about 10 years ago, actually wrote 2 very nice books on symbolic algebra systems, which can lead you by the hand, which show you how much of the guts are set up. But a lot of that stuff needs subtle changes to work with non-commuting. Here we are. I've loaded a file called test. You know, we're computing factorials with numbers which are injected into the expression. So they're turned into constants, you know, they're multiplied, they get canonicalized, and immediately recognizes they can't be much, it's just, you know, a bunch of constants. But this is kind of shows that we can do the same kind of numerical calculations that you expected to do. And A and B and C are three commuting variables, and we take the cube, and well, it doesn't do anything. But it knows about expanding things. And the factoring syntax is slightly less pleasant, because it uses a pattern. There's not a nice syntactic sugar with patterns yet. But there's also, let me show you what else. Okay, X, Y, and Z are three non-commuting symbols. So, again, you see the things been kept in the appropriate order. Something's going wrong there.
Yeah.
Right there. 6x plus z.
Check that. Oh, well, keep going. I resuscitated this thing for the particular demo here, and I may not remember all about how it works. And there may still be bugs. Okay, so, but you know, this is Hermite is a Hermite polynomial defined using the usual kind of recursion relation that we would, you know, takes expressions in, and you know, it gives the appropriate answers. Sure. One should be skeptical of the results that involve expanding powers, because in the process of doing certain optimizations, I recently broke it and thought that I had fixed it. And so this is it. Oh, it's definitely broken. Okay. Well, don't believe what we get from expanding powers. And we can handle tensors. No, it's actually. Okay, what happened there? So G is again defined to be a metric tensor. It's got a couple of indices which I predefined. All right, and when I typed it in, it came back with these other things in it. And D is the textual representation of a dummy index. So it's an index which is marked as repeated, which means it gets summed over in the actual expression. So if
You missed an I.
oh, did I?
Eliminate.
Elminate. The elm is a marvelous tree. There. So it tells it to eliminate the metric, tells it to try and subtract the indices. Oh no, it's once it's reduced to something which is summed, both indices are repeated and summed within a single tensor. It's called a trace, and it knows that these things are defined in a four-dimensional space. So when you say eliminate chronic or trace, it gives you the number 4. So the kernel letter itself, G, when it was defined originally, this Minkowski metric, it knows that we're in a four-dimensional space because I told it to. So when you do these calculations, there's a bit of overhead setting up appropriately I'm operating this space, I need to define that these things, objects, will be indices. But once you do that, it's pretty fast. And in the actual bigger calculation that I have a bunch of helper functions which just speed that along. And I'll show you some in a little while. So that's the that's a bit of the test drive, and I can show you some more things that people want to see afterward. Here's the actual, sort of industrial strength test project that we've done. And so this is a Feynman diagram. Remember, John Wheeler, Richard Feynman's thesis advisor. And what this recommends, one of these diagrams, what it represents is a term in a power series. The first term being, in this case, just the gravitational interaction. This is the first correction to the gravitational interaction of quantum mechanics. All right? So this thing here is like an electron or a proton zipping along, minding its own business. Perhaps it's near the black hole in 1087. And a photon goes whoops off and then whoops back on, because that's how we model these quantum corrections. And just as it hops off, gravity happens to come in from the side and go grab onto it. All right? So that's kind of physically what the thing is telling us. And what behind this is actually an integral which we need to evaluate. The integral will tell us what the first quantum corrections are. It's a good test case for trying to stress test the symbolic algebra system, because from general grounds, I can tell that the answer has to come in the form of 6 different terms times some stuff. So I can already, ahead of time, know the approximate form of the answer. If I get things which don't fit into that, something's really wrong. All right? The calculation to split this thing up into 6 different terms takes a couple of days. You go through, it's like 81 possibilities. You can reduce it to 6 using various identities, and then you can discover that 2 Russian guys did it in 1958. But they made a mistake, so it was good to do it again. So the integral that we're going to evaluate is, well, we're not actually going to evaluate the whole integral. What we're going to do is, this is the integral that needs to be evaluated. What we will do is we'll take this thing here and expand it out, figure out which terms could possibly be non-zero, and then we'll get them at the end. And then by hand, we can actually do the integrals. And there's another thing which you do just before you do it, because you notice that this integral, minus sign here, so there could be a pole in the integrand. Well, we're going to take the time coordinate and multiply it by I, which will basically turn the whole denominator to be positive. Okay, so we're going to do some tricks along the way, but that's not going to affect this thing that we need to expand up here. And to express that thing up there, well, this is how you do it. Okay, so I have some helper functions defined in another file, which do all that vector stuff. There's a function called make tensor, and you say make tensor in Minkowski space in one dimension. Well, they're just going to abbreviate that as momentum and just give it the name. And momentum P prime, so we have another one. So one of the great things about the Haskell syntax is you use prime variable name. It makes life so easy for people who grew up in physics. It's why we're not doing it in most other languages. So there's some masses. There's these 2 parameters x and y, which are in the integral, which just involve getting it into that nice form, nice very symmetrical form. The spinners represent the electron or proton, which goes in or out. There are these funny things called gamma matrices, which have to do with the way things that have spin 1/2, like protons and electrons, interact with light. So when a photon comes along and pops off of an electron, it does it with a probability, what we'll call an amplitude, proportional to some things about the electron spin and momentum times this matrix. And the result of that is a vector, and the photon field is described by a vector, so we get a scalar, which is the actual probability. Well, really amplitude, so I don't have to explain all of physics, that expresses the what's going on. Okay, so that whole triangle diagram, that's, you just write it down like this. All right, so here you got here's the photon interaction. So this is all, you write these things down backward, okay? So the thing which comes in is the right. Do it backward. So here's something which is basically the first photon popping off. In the middle, the vertex, the Bell-Infante vertex is the kind of state of coupling to ground. And Bell-Infante kind of first worked out a nice symmetrical form for it, which people finally thought made sense. And then there's another interaction with the photon going back on to grab onto the electron. And this other thing here is the electron in between having the photon hop off and hop back on. Okay? So that's what these. So you take this, you put it in, and you load, and then what you do is you say expand. You see all the terms. And you get, what you get is, another 38 pages of this. Now, one of the reasons why this is a good test case of a symbolic manipulation system is that there is not it's not just one thing you need to do to this. The terms have different forms and require different manipulations in order to get them into a simple form. In the end, many of them will have the same form, some, but they don't all go through the same sequence of manipulations. Essentially what you try and do is apply Dirac's equation for the motion of the electron by finding momenta and pushing them one way or the other way using commutation relations, which is why we have to handle things which don't commute. Right? So what you do is, so this involves interaction, and you sit in front of your computer, and to do the whole thing, the worst case, right now, these things are taking, if you run them in GHCI, they take 2 minutes. It's not so bad. If you compile them, right now they're taking about 30 seconds. That's with a few optimizations. You gotta go back and check it with power. I don't use it with this. So it can be improved, but generally speaking, you get results faster than you can think about them, which is kind of the, I'm willing to work hard if I'm not getting results fast enough that I can think about them. But once, okay, it's not now, what do I do? I wasn't especially motivated to speed a lot of things up. But I'll show you some more, especially for new folks who haven't seen profiling. I would like to give everyone advantage of my foolish experience in not having profiled first. What do we do? What does it actually look like when we process it? I can show you the whole file, but we do things like this. The Dirac equation is we look for things where, this is a tensor, here's momentum, right? Make pattern units. I need a better syntax for that, but let's have fun. So this just says, I want to match an index, and k is not, momentum. It's just k is anything. It's going to get matched. Right? It's a pattern variable. And I need to find something where this pattern variable and this pattern variable are the same. All right. So notice that here's a minus, and so these are indices, and this one doesn't have a minus. So these are actually being summed over. So look for dummy indices where a p and a gamma matrix are contracted. All right, and if it finds one of those and it's right next to this input polarization spinner, which describes the spin of the incoming electron, then it will replace it with just the mass times that polarization vector. All right, and it's not very smart now, so if these things are, this one's down and this index is down, this one's up, you have to tell it to look for the pattern where this one is down, and this one's up, and this one's down. Instead, give the same answer. Again, it's not that smart. And I can also look for applying the Dirac equation the other way. So here's P prime, this is the outgoing momentum, applied to the outgoing spinner with a gamma matrix with the appropriate pattern. And I replace that by a mass in the outgoing polar-digit spinner. I put all these patterns and replacements into a list, and I say, apply until stable. If you do it over and over again, the expression doesn't change. Multi-match replace. So this is the workhorse of getting all the stuff done. You put in a bunch of pattern replacements, you put them all on a list, say apply them all, keep applying them until you can't apply them. Because as the result, because we do this incremental canonicalization, it may be that in the case, in the course of doing this match and replace, we shift things around, do some simplification, we find another case where we can apply the same equation, right? So we just do that over and over. And then there are a few other things that we do with switching the orders of gamma matrices, and that's about it. It's all pretty straightforward at that point. Well, there's the answer, converted into glorious tech. So it's a lot smaller than the whole 38 pages. However, I told you just a while ago that everything must fall into one of the 6 acceptable forms. So let's check to make sure everything's right. Okay. This thing with 2 L's. Actually, I use L and Q, which are the sum and difference of the incoming momenta. They have the virtue that they're orthogonal, so if you express things in L and Q, some stuff goes away. So 2 L's is good. 2 L's of course is good. 2 Q's is okay too. L and gamma, if it appears symmetrically, is okay. That's a winner. L and Q. Oh, L and Q is a disaster. Something wrong here. And the metric tensor is all right too. Well, okay, that's a problem. Well, here's L and gamma again. That's good. It appears symmetrically here. I didn't quite factor them all in the same form. Q and gamma. Oh, another bad one. So something's gone wrong. Or maybe not. What's actually happened here is what has to happen at the end is that when we do the final calculation, anything that doesn't fall into one of the 6 forms has to vanish. It turns out if we look a little closer, the bad terms like this Q gamma thing, Y and Z appear antisymmetrically. Y and Z antisymmetrically. And also the other bad thing, the kind of QQ thing, all right? QQ is okay. Here's the other one, Q gamma. Yeah, this one here. If we look again, let's see. Yeah, here with like 2m squared, y squared, minus 2m squared, z squared. Y squared, so these appear antisymmetrically. When we go through them all, yeah, so those are antisymmetric. Those are antisymmetric. Remember that? Is integrals over y and z. That's a nice, basically the region integration is kind of triangular shape, symmetrical, z-axis. We can prove that anything that's antisymmetric in y and z will vanish. So in fact, after doing the complete integral, the bad terms go away. All right, so we really have, thus far, been able to have some confidence that we're getting the right answers from the system. As a further check, and in part to get some of the speed issues worked out, the original scheme for maintaining the dummy indices, making sure they were always consistent, was replaced with one which actually made sense. The original one was a real kind of stupid hack. It did work. It was kind of hard to explain the rhyme or reason behind it, in addition to being an n-squared algorithm. And it was replaced by one which is principled. I can explain to you how it works. The explanation will be more convincing the more beers you have, and less convincing the more beers I have. But now it kind of makes sense. It's based upon a dynamic programming algorithm, as you kind of would imagine that you want to bubble up from the leaves of the expression tree and pair off things as fast as you can and defer decisions as you go up. Okay? So I was convinced. So again, I was convinced I was going to change the slide. But I was convinced that the big problem we were having with this thing, the reason why it was taking 2 minutes to calculate stuff, was it was re-simplifying things over and over. So that's what it does. It's not very smart. It doesn't check, oh, I've simplified that, won't do it again. It just blindly says, let's just make sure it's nice and simple. Always. It's not it. Kind of embarrassing. It turns out that the biggest, after I fixed the dummy index maintaining system and managed to get things to speed up roughly by a factor of 4, the dumb routine I was using to, whenever I want to change an index, to reach down the tree and change it, is miserable. It's utterly miserable. It's kind of got some debuggish stuff left in it, but it was working fine, and until I fixed the algorithm for maintaining dummy indices, it wasn't showing up as being horrible. But for people who haven't done this, once you do a profile and you get into a function, you say, this function is the problem because it's consuming 81% of the entire time my program's running. This function here, replace index. Var index in context is just the index that you're looking for, and essentially a bunch of constructors which say, at the first sum, look for term number 3, the first product, look for term number 2. It's called a breadcrumb trail, and it tells you where to look in the tree. All right, so I give you an index with its breadcrumbs. You go down the tree and you fix it, change it to another index. So it looks for, here's the var index, it looks for the breadcrumbs, here's where it is, and it spits out something else. So here it's looking, how much time is it spent actually messing with the tensor itself? You actually reach in to that index to reach in. And what you do is you put in this thing, SCC, or it's a cost center annotation. It says, I want to know how much time the function spends from the point where I stick this funny thing in comments, and it goes all the way to the end of the expression. These cost center annotations, basically they go as far to the right as they can. So I made one here for replace index 1, here for 2, replace index 3, replace index 4. And that will give me an account. Every time I go into this function, when I have profiling turned on, it'll count, well, how often am I going here? How many allocations am I doing in this bit of code? How many allocations am I doing here? How much time am I using? And that will give you sort of a detailed look into how your code is spending its time. All right? It's, if you have enough, especially with libraries, I know, look, here's what you have to do to get profile. The other thing is, when you install the Haskell platform, make sure you install all the profiling libraries. We have argued, there have been rather heated arguments about this ICMP and Haskell implementers workshop about, some people complain, when the profile, it just takes so long to do section compiling. It's like, and the first thing we do is tell them, you have a problem, have your profile, but we don't ship them with the profiling libraries. Build all your stuff with profiling turned on. Install all your packages with profiling turned on. When I was maintaining all the MacPort stuff, every library had its profiling turned on when you got it. So you could profile. And in fact, that was one of the big things we did. We actually made that change for darks, when darks was having their horrible problems with performance. They had algorithm design problems too, but when they were having their simply implementation problems, we got it so that they could build GHC, get all the libraries in profiling form so they could profile. But you can't profile your own library unless you build it with profiling turned on. And the way you do that is you enable library profiling when you configure it. And also, the other thing you need, GHC option auto all, which means to put automatic cost center annotations in every function. You saw I put a few specific ones in there for things which I thought were maybe hotspots, but this puts them everywhere. You need this. If you just turn on enable library profiling, you don't say auto all, it doesn't tell you anything about what's going on inside the library. It said, whoa, I went to the library. It will build as profiling. It won't give you an error message, but it won't actually give you any information about your library. Okay? The other thing is, and near as I can tell, it's still true. You configure it with enable library profiling and GHC option auto all, but if you just say GHC install, it forgets. So you got to do it again. All right? Once you do this, profiling is on. Then you must build your program with profiling. So here's, again, this is top secret from my place of employment, so we made it too small to see. Don't worry, I've already given version of the slides as a PDF, so you'll be able to see. But what you do, all right, so here we're going to build the scalar term of the triangle function. We say GHC make dash profiling, all right, dash proof, dash auto all, minus optimization 0, start with minus O 0. That way, your errors, your hotspots will be in the places you expect. The higher level of optimization, you shuffle things around and make it hard to figure out what's really going on, especially if you're trying to do fancy stuff with lists and things, and operations which get deforested. Then you must say minus RTS ops, which will allow you to turn on profiling when you run your program. Otherwise, it will annoy its runtime options. I don't know why you have. I think you should always take runtime options, but someone thought differently. The output name and your function. So it builds it. So we have some utility functions. We have the main thing. Then you say your program plus RTS minus P. It remembers everything it did. In fact, it remembers it to the tune of about 38,000 lines of profiling information, about every one of which just says, I don't spend a lot of time with this function. Which especially happens if you have a big library and you're not exercising all the pieces of it. But looky there, well, those things here, this is all about the place index. They're using goodness knows, well, my goodness, 91% of the entire time. So, I ought not to be worried about my expression being multiply simplified yet. Everything, all the bad stuff is the indexes are getting constantly replaced in an inefficient way. So that's what I need to change in order to get the performance check. We can also, one of the other good things which happened when I changed the initially really stupid algorithm for finding the dummy pairs is that the memory behavior became much better. And I think that had a lot to do with the kind of factor roughly 4 speed up that I saw. Once you have compiled your program for profiling, you can check that immediately. Instead of saying minus P for getting your textual profiling, say minus 8C, and it tells you about the memory behavior, heap and cost centers. Let's keep it in mind. What happens is you get this output file called yourprogramname.hp. You run HP to PS on it. Minus C means use colors. Still makes PostScript. Everyone loves it. And you have to use an explicit redirection because it doesn't know about output. But then you get a sort of nice heap profile. And this is a nice heap profile. See here, byte allocations of 6 megabytes. That's so nice compared to what it was doing before. Before it was kind of this parabolic. And so the kind of allocation times time is 110 megabyte seconds. Before it was like it was many gigabyte seconds. It was actually close to 100 gigabyte So this is doing crazy stuff. So this is actually a fairly well-behaved heat profile. Nothing's blown out. You know, some bits here when I do certain operations. Well, particularly near the end of the processing, I'm finding lots of things which are zero. And so what's doing what we're seeing getting really busy in the spike is delete expression. Okay? So as it actually simplifies, it's saying, oh, don't need that, don't need that. I can combine these. It starts throwing things away. So generally speaking, this is all replacing this stuff here. So essentially, if I get this fixed, you'll have extremely nice memory behavior. It's doing a non-trivial task. It's all good. Aside from being slightly slow. So a lot of break in just a second, but let me just give you the status of the library. It's being actively developed. I've broken it a couple times in the last few weeks. I'll put it on GitHub as soon as I fix the extension times. I thought I actually had it fixed. I realized I had busted it severely a day ago, and evidently I did not entirely fix it. So it can do real problems in limited domain. That triangle, actually, there's some kind of interesting physics there. If I replace the electron with the neutrino, there will be other terms which are really interesting, which physicists will be interested in. Folks who improve on gravity. It still has performance issues, and I'll talk after the break about how we're going to make it extensible, because that's still a problem. How can I make this so that other people can easily extend this work? Everyone needs to have a drink of water.
Real fast.
Yeah, go ahead.
When you said performance issues, I'm not sure, but if there were other tools you could use to do the same kind of thing, is this slower or faster than those other tools? Because if it's already faster, then like
the answer is that it's pretty good. It is, as near as I can tell, it gets the correct answer faster than the other tools. I mean, honestly, I tried Maxima, just open source. I figured, well, if I go to change, I can fix it, and it's got issues with dumb indices. Cadaver. It was great. It was like, stop on the gas, go, don't turn it, but if the road does, and I could never really, just making everything work, say, in Mathematica with X-tensor was just too daunting because the programming paradigm was so different. Now, I guess the performance issue is that, I look at this thing and say, oh crap, I'm speaking to you, you spent the time doing that. So it's more the kind of okay.
So one thing that is coming to mind in terms of the performance problem is, have you looked into using like data reify or something to tease out, just construct the shared sub-expression representation? And
I also, this will be related to what I talked about just after the break. The final interpreter representation has been used to do a lot of interesting stuff on optimization of storage. All they did is like DSL. So basically one of his demos in the lecture course he gave was to optimize hardware expressions to maximize sharing.
Whose lectures?
Oleg Kislov's lectures on titled spinal interpreters. There's one set which was hardware oriented. He's got two. It's kind of a generic set, which is mostly software oriented. But the other one was how could you say encode hardware operations and force it to share the hardware representation. But I'm going to talk about that right after the break. So why don't we take a break? So take 7.5 minutes. Problems of trying to make libraries like this extensible so that other people can take my work and add stuff to it. They want to have it handle other kinds of algebraic objects. Maybe someone wants to add polynomials. Everyone loves polynomials. Polynomials are a finite field, so people can do crypto. the library did actually go through a phase where it had a polynomial data type that could manipulate polynomials. Actually, as a kind of experimentation. What?
The screen seems off.
The screen seems off. My screen is on. Oh, well. Let's
really on.
see. It is.
We're both off, so that.
We get pulled out.
Oh, sound!
Well, I don't want you to turn the screen on.
All right. I'm wondering if the screen is actually turned on. It's just a magic little.
Oh no.
No, it's not the screen because we're.
Yeah, it's both screens is the issue.
Well, let us see if we.
Oh, you're
Hold
right.
on.
It's waking.
Got something?
It's waking up. Yep. All right, we'll
Yeah, oh, that's funny.
check this way. Wait. Oh, let's go. Something's happening here. Interesting. Wait a second. Okay, while we're waiting for this, I think something's happening. A physicist, well, no, it's a mechanical engineer, an electrical engineer, a chemical engineer, and a computer scientist are driving in a car. And the car, made a bad sound and ground to a halt. The mechanical engineer said, broken crankshaft. The chemical engineer said, fuel contamination. The electrical engineer said, no spark. And the computer scientist said, well, maybe if we just all get out and get back in again. That works. Built the screen. There we go. We get a little Star Wars, hyperspeed effects. Okay, there's a problem in making things like this extensible. And to some degree, for the symbolic mathematics problem, it's particularly acute. And it has a name, it's called the expression problem. It was named by Phil Wadler, great hero of functional programming. It should be like this Stalinist medal, hero of functional programming, that we give to the heroes of the field. But so it's a new name for the whole problem. We want to define a data type by its cases, or an algebraic data types, and we're going to be able to add new data types, to extend those, put in new functions over the data type, and most importantly, we don't want to recompile existing code, and we want to keep static type safety. We might be willing to compromise on static type safety, especially if we could avoid recompiling existing code. The key thing for things like extending this library is how can you write a module which say adds polynomials, maybe adds certain finite field operations to my base library without having to get in and mess with the expert data type to add to it. Okay? That's the expression problem. Functional learning. And it's particularly acute in things like symbolic mathematics because on the kind of axes of functional programming is this way, object-oriented programming is this way. Object-oriented programming makes it hard to add new operations, but easier to add new objects. And that is probably the more common case when we're doing symbolic mathematics. So maybe this is one kind of bad thing about doing it in our favorite functional language. And basically this so it says, again, other operations you might want to do or add things like addition, multiplication of vectors and matrices, and say a linear combination data type. That would be really good for a lot of engineering applications. I'm surprised that no symbolic math system has a linear combination type. Not even axiom. It's got lots of polynomial types. Again, the IBM guys were all worried about crypto and finite field arithmetic when it was being developed. But no one has like linear combination. So here again is the expert data type, and we'd love to add something to it. The symbols are defined, and I might not even want to mess with that, right? What I did was I kept the expression data type in one file, and I made the symbol data type, and I extended this, so I didn't have to go back and mess with the core expert. But I still, if I wanted to add to this, I would have to go into the code and edit this algebraic data type. All right? So you again have to go into the code, edit, recompile. How can we avoid it? There are three approaches. One of which is called add the universal type. It's like, don't be proud. Throw away static type safety. What good did it do for you anyway? Make things instances of dynamic, which packages the object and the representation of its type. And so you have something which is dynamic, then you can, you can put it into functors, right? Everything's dynamic. You don't know what it is, and you figure it out at runtime. We're already deferring some stuff to runtime, so maybe it's not such a bad thing to do. It does feel like cheating. And if we could, is static type safety, even though you kind of make it, it's a good thing. Make sure that it's a little theorem which gets proven that at least some bit of the interface is right every time you compile the program. All right. And even when I was at a startup company and I was running, we made network test equipment. And so we had to try to be better than the customer's network equipment, otherwise it was sort of embarrassing. But even when we were writing all this, high performance networking code in C, we made sure that people got the right. No one was allowed to cheat on casts in functions, and we tried to enforce as much static type safety as the admittedly, kind of poor type system, the weak type system of C would allow. It seems to help, and we want to keep it. Or we have what's called the final interpreter representation, which is a way of changing that data type around and turning the data type into functions. So I'll talk about that a little more depth. It does a lot of things well, and then falls down with a very important case for symbolic mathematics. And then I'll talk a bit about products, Mulder Spearstra's data types a la carte, which is actually a pretty nice solution, although it takes a while to wrap your head around, which might actually get us to where we need to be able to extend this kind of library. All right, final interpreters replace data constructors with functions. All right, the name final comes from this kind of distinction. We have the initial form is like, well, what you would get when someone typed it in, and you would build up this abstract syntax tree, and there'd be type constructors telling you what everything was. So you have constructors telling you what things are. To what Oleg Gustelov thinks is the final interpretation, which you replace all those constructors with a semantic function. So saying the constructor add, it's the function add, which does the addition. Okay, and you can express this. You can change your syntax tree from having these constructors into this kind of bunch of functions which get applied. And he calls that the final representation. Now, of course, the only thing you can do with a bunch of functions is give them, to make instances of them and give them an interpretation, so when you walk the tree, something happens. All right? But a lot can happen. So, here's his extremely simplified data type, just to try and, make this concrete for everyone. This would have, here's our, really, this is kind of when my daughter was 2 years ago in school. This is her symbolic mathematical system. It involves literal integers and addition. Okay? She's up to multiplication. Now we're going to replace this data type with this class, where we'll have expressions in some kind of representation. It's kind of a way to have multiple representations. And we can take a literal integer and inject it into a representation. Then we can take two things in this representation, add them, and produce a third thing in the same representation. Okay? So what we need in order to actually carry out the operations are instances. All right, so literal, so the interpretation, representation, which yields an int at the end is actually the interpretation which evaluates anything made of multiple applications of literals and adds. All right, so add will add whatever it's given, actually add the numbers. That takes two integers and the literal will just give you back whatever it was applied to. The nice thing is, and the reason the class was parameterized with the representation is that we can have more than one interpretation. Okay? So we can have a string interpretation, which will be the same as a show instance, really. So it takes a bunch of these, it takes any expression made up of literal and add, and instead of evaluating it by turning the literals into the number they represent and adding anything that has to be added. We'll show the numbers, and we'll print out the numbers with a plus sign between them and parens on the outside. Okay? So we have more than one interpretation. One of the great things about it is that the lovely thing about it is that this solves part of the expression problem in that it's easy to extend. Okay? So, my daughter is now in 3rd grade, so her math abilities have added the class multiply expression, which again has a representation and a new function, mul. And we have to add instances of it. So when we want to do the int interpretation, we multiply the 2 inputs given, and we want to have it show something. We print the 2 arguments with a star in between them, wrapped up in parens. All right? This is great, right? It works. We've solved the expression problem. However, the one thing you can actually do with this kind of representation is easily extendable. It's very easy to do anything that's basically a form. Anything that requires you to kind of start with the initial value, walk through the tree, folding things up, and get one thing out at the end. What we need to do in symbolic mathematics is take something represented by one of these lists of kind of expressions of add, mul, and literal, and convert it into a different one, where we've done some kind of simplification. And to his credit, in his lecture notes on type tagless final interpreters, it's in the references at the end, he shows a very simple example. Bullet shows a very simple example of how to do this by essentially pushing negation as far down into a structure as possible. So you can actually make an interpreter which this parameterizing yields another expression. It's hard to understand just how to say push negation in through parens. The lack right now is there's no automatic way to say take a bunch of pattern matching and distill that into something which you can then apply as an interpreter, which will yield a particular set. All those simplifications together. Remember the call tree I showed? That's what I need to do. I need to do all the things in that call tree graph that roughly dozen functions, some of which call themselves, and a few call others recursively. And no one knows how to do it yet. So it is when we give up pattern matching on the trees, we give up a lot. Pattern matching right now is the easiest way to deal with anything where I have to say, I need to do something based upon this node has this and this node has this other thing. And when you start looking at more than one node at once, life becomes difficult. In principle, he has shown that these problems can be resolved. In practice, your head will explode unless some progress is made in finding a better way to do this. There is another approach, which may be a bit better for handling the expression problem with respect to symbolic mathematics. And that was introduced by 5 years ago by Winter Smearstrap in his paper Data Types a la carte. Phil Wadler said it was the best solution he had seen so far. And so what we're going to do is we're going to keep data constructors. We're going to use a functor, which means we're going to have to find something which we're going to have a structure which can only take a single data type, but we're going to have this really cool data type, which is a coproduct type, which allows us to say the type of something which could be this type, or this type. All right? And that's pretty close to what we want. Okay, so I know this is going to go fast and be hard to wrap your head around. That's why there are references at the end. And this example is basically stolen directly from my file where I typed in everything in that paper to try to understand it. So I have this is my expression type, all right? So this is the generic kind of fixed point functor construction. That's why this is native data. It's hard to talk. I can say things like the generic fixed point. Okay, see, we're slightly in hyperspace since the brain. So basically says you can have a thing and underneath it are expressions with things. We're going to have data types which are values. They could just be ints. We'll have another data type which is an add, and this constructor will add two things. Because they're going to get stuffed into this functor, they're going to need instances of functor. That's all pretty straightforward. The nifty thing, as I said, what we need to make this work, to make this an expression where various pieces of it have different types. There's only one type there. There's only f. We need to make f the type which says I could be an object of this type, or this type, or this type. All right? That's what we need. Now, the thing which is either this, or this, and not overlapping, exclusive, is called a coproduct. All right? And we're going to use a type operator here. There's a bunch of GAC extensions that you need to turn on big here. GAC, I will tell you which one to turn on. And essentially what we do is you say, well, the coproduct of these two types is, well, we're either this one or that one. And rather left or right. Essentially this is a kind of tuple construction at the type signature level. All right, and if I need to add something else, I'll just stuff it into the right-hand side, so it'll kind of grow. And so what I'm effectively doing is I'm just making a list. And it's cleverly concealed with these kinds of constructors, but I'm making a kind of, like a Lisp-style dotted list out of my type, in the type system, okay? And then I need to, say make these things instances of functor as well, so we can push operations down on them. And then we're going to have, it's a functor, so we can fold, right? Everyone loves that. Okay, so now we have now the nice thing is we can treat every node the same, right? Because they all have the same data type. They have this coproduct type. And we can make the evaluation algebra, which will tell us the answer, what does the expression evaluate to. For values, it just pops it off. For adds, it does the addition. Okay, and for more complicated things, it figures out what it should do on the left and the right. So you have a coproduct type that's not just one of the simple types all by itself. It simply applies the evaluation algebra to the insides. All right, and evaluating an expression is great. You fold the eval over the expression. It's wonderful. The expressions are not wonderful to contemplate. Okay, that's not a big deal yet. You'll see on the next slide that we can do some stuff to clean them up. Because what you have to say, well, stuff it into the functor, and on this side it will be this one. Why is it?
Your head is in the way of the sensor.
Oh, my head is in the way of the sensor. Okay. All right. So, well, let's look at the type signature first, because that actually gives you the most information. It's an expression that has values and adds in it, okay, connected by this coproduct. And this whole thing is the type. All right, so every node has the same type. Now, to realize that, you have to have this ugly structure where you stuff things in the left and right leaves of this coproduct structure. We put the whole thing in a functor in wrapper, but you can do it. And stuffing things into that form can be automated. You can do that by some smart constructors. One thing you can do is this is really clever. So you have two functors, and you say one is essentially a subtype of the other, and you define an inj function, a short inject, which will inject a type of the subtype of the superfunctor. Okay, and the instances of it, well, if you're trying to inject something into itself, well, of course you can. It's a subtype of itself, so you don't do anything. Okay, and if you try and inject something which is a subtype F into something which is already a coproduct type, which has F in it, well, then it's just it's already on the left. And if you have something which you're trying to inject into a coproduct type, and one of the things in there is already a subtype of, you stuff it on the right-hand side and run the injection on what's below on that side of the tree. Tree grows to the right, but the list grows to the right. Okay? The usable version of inject for the user just says, well, if I have some of the subtype of another thing, I can make a functor with whatever is inside inject. Essentially, what this allows me to do is make this kind of ugly addition operator, which will take, as long as add is a subtype of the expression, will allow me to add two things by injecting the add constructor. And I can do a val by injecting the val again, as long as val is a subtype of the overall expression type. And playing with these things, you see that they're kind of simple. It does all the kind of action going on at the type level. I find very confusing, and I understand it for periods of 25 to 28 minutes at a time. And usually when I just play with it in GHCI. But the key, even if you have trouble, following this, the key thing is that code products allow you to define a type, which is the type of something which should be this type, that type, or that type. All right. Now, so one of the big problems of this issue where we have pattern matching and trees, and we want to be able to do things like that. Co-products can get us much closer to that goal than the final interpreter approach. All right? The payoff is the short inject function is a partial inverse. It's misspelled here. It should not perf. It should be project. Short project. And it lets us find out if, well, for a supertype A, maybe it has a subtype. So if it's not a subtype, you get nothing. And if something is a subtype of a supertype, then you can get it back. It's the same subtype. This allows you to define a match function on that functor. Okay? And what it does is it doesn't essentially looks and sees, well, looks in that kind of list of types and says, well, is that the type that's there? What it looks at something in the functor and just projects. All this stuff, the magic all happens when you stuff match into an expression. There are types around for the compiler to try and figure out. It doesn't make much sense. It's just sitting there by itself, right? You can do this to do basically distribute multiplication over addition at one level. What we do is say, well, match the input expression. All right? The input expression has to have, well, some stuff which add has to be a subtype, and mul, right, because we're doing distribution. So match it. And as long as, mul A and B is good, we're in the maybe monad. I promised I wouldn't bring up monad. But
I promise you almost wouldn't.
I told the truth. Good. Oh, well, I'm not as dishonest as I thought. So what's going to happen is this will all be short-circuited if anything returns nothing. We get nothing out at the end. But as long as you're getting something back, maybe as a monad, it just keeps on running until something returns nothing. So we'll extract A and B. We'll match for B. We'll get, as long as that is two things which are added will return the distributed thing. You have the downside in this case, at least in the examples, that these things haven't been bodged into the num type class so we can use plus and times, like you actually eventually like to have the user do. Because defining new operations that essentially replicate existing operations is, remember way back when 2 hours ago nearly, the desiderata, the user is not a compiler. Okay, but that kind of stuff can be generally taken care of if you're suitably disrespectful to the designers of the prelude. So it's good, and the downside is to make it work nicely. Now, all of your code, which is at the moment expressed functionally, pattern matching, ends up inside of monadic constructions. If we can limit it to a fairly small bit of the library, maybe it's just worth it. Okay. In an ideal world, the parts of the library that actually muck about with the insides of the data structure should be fairly small. And everywhere else, you should be using plus, minus, divide. You shouldn't be messing with the data structure. You should be doing math. When you add something new, yeah, you got to get into the internals of it. So maybe we can live with that. Then there are some other possibilities. The latest iteration in extensible records, using the wonderful features of 7.6 GHC, will allow you to do some type safe casting. So you can again make something which is you can essentially make something have a less general type and do subtyping on that. The nice implementation uses the recently introduced symbol data type, where you say, this string makes the name of a new data type. So you can name data types whatever you want now, whenever you need them. And that's made a lot of things which used to be kind of hard. You have to do hacky stuff. And in order to understand the hacky stuff, you had to be, like Isilov, now mortals could contemplate. So maybe that's enough. We don't have to go there for these really fancy things which also are designed to address the expression problem. Okay, for further reading, and two good books on the guts of how symbolic mathematics systems work. If you ever wondered, if you don't know who Oleg is, he lives in the type system. He makes the type system job, and he likes the fact that, in fact, particularly the older version of the type system, which ran on unification, was essentially an implementation of Prolog. So you could do any calculation you could do in Prolog in the type system while the compiler was running. The current type system is based on constraint handling rules, which does have the advantage that it produces occasionally understandable error messages. And I recommend that everyone read Ultrasphere's paper on data types and all the card and play with the stuff, because it really helps you get your head around some things that are very powerful and you might find useful in your own work. That's it. Thanks for coming by, and I'll be happy to take your questions.
Sure. So one thing that I'm just thinking I need to stare at now is, how does this relate to a lot of machine data manipulations that come up here are kind of related to what you see with combinatorial species or analytic algebraic combinatorial things.
Yeah.
Is there any interesting connection you want to show that as far from your perspective? Aside from yes, there was some.
No. The answer is yes. There are a lot of things with combinatorial species. You should be able to, combine. You should be able to do many of those things. Perhaps some of the facilities with the Wheeler package. Well, a lot of the stuff you can do in raw, Haskell. I think Brett Yorgi did a lot of the stuff in his talk in 2 years ago. A Haskell symposium in Tokyo. He was common for the species, I think.
There's a Yorgi library for it, but
Yeah.
but yeah, just
No, I'm actually, I had a reason to use that kind of stuff in anger once for a commercial project.
Awesome.
It turned out that in my day job, Alcatel-Lucent, a telecom company, not dead yet. We're getting better. But we make wireless communication systems, and so there were some questions which had to do with mesh networks. We have multi-hop. So you send a radio signal from this base station to that one, eventually it gets to the user, which involved enumerating trees. And we needed to figure out the number of trees of certain, the mean number of trees of certain depths. And we actually spent quite a bit of time trying to, you can define a polynomial, okay, which is the number of trees of total depth L, where L is the sum of the depth from every node in the tree to the root. Okay, so usually the depth or height of a tree is the length from the deepest node to the root. This is we call the total length, which is the sum from every node to the root. And that had relevance to the amount of data traffic that was flowing in a wireless network. And you could define a polynomial whose coefficients were the number of trees of given total length L. And we never found, what we were looking for was which would have made all of our calculations simpler, we would avoid a lot of approximations, was a generating function for that polynomial. And I gave it to my friends at IBM, and they couldn't stop them. Well, it wasn't important enough to work too hard on it. Apparently it's somewhat complicated. There's approximations based on the Lambert W function. Now you can do some tricky things where you say, well, this is discrete mathematics, but let's just pretend that the number of nodes is continuous, and then you can kind of make some interesting approximations which are then solved by the W function. Other questions? Sir?
I had 2 points. The first is you can go into your .cabal folder and change your cabal settings and enable the flag library profiling equals true.
Yeah.
And then when you cabal install everything from now until the end of time, it will always install it with profiling, and that's the first thing I do whenever I set up Haskell installation. So just extend that. The second is that you mentioned like a lot. He had 2 co-authors on the Taglis paper. One is Ken Shan, who does a lot of Haskell stuff. The other, who's actually the guy who was initially inspired to figure all this stuff out, and sort of pushed the other two to, helping him figure out how to do it, is a guy by the name of Jacques Perret, who was the lead mathematician on Maple for many, many years, and this is in fact the reason he started looking at this stuff, and he's since jumped ship to the Haskell community. And he's got a lot of great papers on symbolic algebra that have very little to do with Haskell, but they present things like a canonical version, a canonical metric by which to judge whether or not you're simplifying an expression, which is a very interesting problem, because there is really no right answer to when you should apply a simplification. But he produces a metric that actually works like a metric should. And therefore, if you're interested in computer algebra type stuff and this sort of stuff, I just recommend everyone look at all of Perret's papers as well, because they take all that experience from Maple and then they bring it to the
I'm not sure. I think the lecture notes may only have all these things.
I think they do. I just want to
Yeah,
represent
no,
for
but the Ken Shannon correct me was really good too. And there is furthermore another paper, Graham Hutton and I think one of the students, about applying data types a la carte concepts to compilers. And I didn't know about it until I was getting ready for this talk, but I looked at it, it looks really good.
Modular operational semantics.
Excuse me?
Is that the modular operational semantics that just add Skeleton and Python? Is that what you're talking about?
I don't remember.
I suspect that might be the one.
It could well be.
Python and just Skeleton. If I could add to the further reading, Cook and Oliviero with their object algebra is another thing to look at if you're interested in information.
yeah, Bruno Oliveira has a number of papers going back quite some time. This collaborative demonstration. Other questions? Your brains are full of math now. You will sleep well. Thank you again.